All right, it's 2 o'clock, so we're going to go ahead and get started with the last talk in here before the afternoon break. This talk is titled MapLibre Native Upgrade and is presented by Steve Gifford of Wet Dog Weather. Steve?
All right, thanks for joining us. Let's dig in. All right, so I'm going to talk a little bit about, I'll try to skip through the slides that Yuri did a good job on before, talk a little bit about who and what MapLibre is, and spend more time on the native aspect of it, and talk about what the problem was that they were trying to solve, how we've solved it, and what may happen next. You just saw a version of this slide. Having come into the project not as a contributor, but more as a hired consultant, it's been interesting to see where the gravity of MapLibre is. And I'd say in terms of contributors, more European, although that's changing as time goes on. But a lot of the money tends to come from American corporations, although there's a fair number of contributors from Europe as well there. So it's an interesting combination of volunteers and corporate sponsors and things like that. Now, you probably know about, of course, there's more than just these two toolkits, which Yuri went over in the last presentation, but the two you've probably heard of are the MapLibre Web, that's MapLibre GLJS, and the MapLibre Native Toolkits. And what those are, again, those are the last open source version of the Mapbox GL toolkits before they went closed source. So essentially a fork of those, which has got renamed to MapLibre and has since gone on to kind of take over its own destiny, become an open source project, and move onward from that fork. So in terms of popularity, the web version is actually doing quite well. Lots of contributions, lots of users, and we saw a lot of probably what were MapLibre maps during sessions here. And I see them in the wild all over. People are switching over as they may want new features or what have you. So it's a very healthy ecosystem around the MapLibre GLJS. Less healthy around native. So by native, we mean basically the version of the toolkit that runs on iOS and Android, and also a few other things. iOS and Android are the big ones, the mobile versions, but it also runs on Qt. This is the version that powers the Node.js, tile rendering thing. It runs on Windows, it runs on Linux, and it's used for a variety of random things which tend to be important to some of the bigger sponsors, but maybe less visible. So in terms of health, there were some problems for the native version. So the problem was basically technical debt. And I like to cite this as an example of when someone actually had to take some action on technical debt. Usually we just let it go and let it go and let it go forever. And here they actually had to do something. So back in the old days, we used OpenGL ES for rendering. Now, of course, everybody loves OpenGL. It's got open in the name. It was great. It was great for a long, long time. The problem is, at least on Apple devices, they introduced a new rendering SDK, Metal. Now, OpenGL had gotten pretty old. It wasn't really reflecting the way modern GPUs worked. And so there are these new APIs, SDKs, you might say, to address that. Apple introduced their own called Metal because they're Apple and that's what they do. They then deprecated OpenGL a few years later. And it's never been clear exactly what that means until now, when we know they're dropping support for it in the next version of their next OS, Vision OS, which is the operating system for that headset. So they deprecated it, and what that means is that you're sort of in an uncertain territory on their devices. Is this going to continue to work? If you do development that you knew that you were slowly losing all your tools for debugging and analysis and so on. So in a sense, it was already not working that well, particularly for development, but were they going to lose it? Were you going to lose it on the next version of iOS? Nobody knows, and Apple isn't going to tell you. So it's hard to make those decisions if you're running like a multi-million-dollar development team. Do you depend on MapLibre Native, or do you figure out something else? So that was the problem. So there were a lot of solutions discussed within the community. Doing a real-time translation layer is an option. There actually is one out there called Metal Angle. And it'll work reasonably well. Do you transliterate the shaders and try to do something fancy around that? Maybe rewrite it all from scratch. Who doesn't want to rewrite it all from scratch? Not me, but I'm sure lots of people would. Maybe do it in Rust. Why not? Just hope for the best. Actually, hoping for the best is the main strategy that most users were kind of pursuing. They were just kind of hoping somebody was going to solve this for them. Now, back in an old startup of mine, we used to have a phrase for when our salespeople would start to get creative. And sales is not really a place where you want people to get too creative. So we would tell them to think inside the box. And the obvious thing here, the thinking inside the box, was just implement the Metal SDK. And that's what they decided to do. So this was done in multiple phases. Since this is a community, and a very new community as these things go, there was a community engagement process, and that involved 4 different groups. Stamen, who has a great reputation in open source and in the geospatial community in general, they kind of did the organization, got the people together. AWS had the money, and they brought, well, money. And MapLibre was the community. So we kind of went through this process where, and us, and I'll explain how we got involved in a minute, went through this process where we put together proposals for both moving the, essentially solving the problem with Apple, moving the toolkit over to the new rendering SDK, but also fixing a bunch of other stuff while we got the hood open, so to speak. So 3 of those groups make sense. Again, Stamen has great reputation, AWS has the money and the need, the community is the steward of the toolkit. Who the heck are we? Well, we're primarily a software as a service company. This is my company, Wet Dog Weather, and we make a product, we sell that product to our customers, but we also have a background in geospatial rendering. So we used to own this competing toolkit, well, still own it, called Whirliglobe. It was a competitor to Mapbox, and if you haven't heard of it, that's because Mapbox won a long time ago. We made that OpenGL to Metal transition many years ago, and in fact, I thought we were doing it kind of late, but MapLibre really pushed it to the edge here. So we understood how to do that. We do things like vector tiles. So we kind of got how to turn an open source geospatial renderer into a metal-based open source geospatial renderer, how to support multiple toolkits or multiple SDKs at the same time, all that good stuff. And best of all, we never really looked at the Mapbox GL internals. I have this very strict view that you shouldn't figure out what your competitors are doing too closely because you'll miss your own opportunities. It's best to just listen to your customers and build what they want. So our toolkit looked very different than Mapbox GL or MapLibre. And as a result, we were kind of a good candidate to help upgrade MapLibre Native. After that first phase where we got everybody together and figure out what they wanted, we designed a 2-phase plan. So the first phase was to modularize the renderer. Say that one 3 times fast. I always trip over it a little bit. Basically, the idea was to create a toolkit, a native toolkit, which could support 2 different rendering SDKs at the same time. So you could do OpenGL, which you're always going to need for Android. Even with Vulkan coming along, there's always going to be something that needs OpenGL. So that needs to continue to work. And also support the new Metal SDK at the same time. And again, while we're at it, maybe modernize things a bit. This toolkit was designed a decade or so ago, and there are a lot of things that you would do differently if you were to do it now. Also, we're starting with a brand new team. This is a multi-component team. I'll explain who contributed what as we go. We needed a way to warm up the team, essentially do a set of engineering tasks where we could get a sense of who was good at what without diving into the complexity of real-time rendering. And we had a bunch of secondary goals, which I'll talk about in the phase 2. So once that phase 1 was done, we got the modularization done. The main goal basically was just Metal rendering. We wanted to be able to use Metal as a complete replacement for OpenGL in what's known as direct mode. Now, this gets a little bit into the specifics of the way GPUs work, but basically, modern graphics processing units look very different than their forebears did 10 or 20 years ago. They're very intelligent in their own way, but they work in a very parallel manner. Typically, these days, you don't tend to tell them to draw a polygon. You tell them to draw 1 million polygons or 1 million things, and they just sort of figure out how to do it. You don't really want to give them piece-by-piece information, and if you do that, it tends to be very slow. They're often drawing multiple frames at once. They're often encoding things for themselves. GPUs have gotten very smart. Direct metal rendering is the closest thing to OpenGL, where you're telling them to render 10,000 polygons at once with this set of colors and this set of values and other information. So that was the first goal, get it over to that. Secondary goals included moving things to the GPU. If you're looking at a 2D map, a modern 2D map, you might notice that the width of the lines changes as you zoom in and out, or the colors of various polygonal outlines, those are going to change, or symbols will get bigger as you zoom in and smaller as you zoom out, and they might completely disappear. All of that should be running on the GPU. I'll talk more about that. It actually wasn't before, interestingly enough, but it ought to be running on the GPU. It's a very simple set of changes that you can make on the fly, and the GPU should be doing things like that. If you were to design it all today, it would be. So that was a secondary goal. We wanted to try and address threading. So on modern devices, mobile devices, you have a lot of cores now. You've got a lot of individual threads that you can run at once. You should be doing most of your work on other threads. We wanted to be able to replace shaders, those are the programs that run on the GPU, and add new layers to the system without recompiling everything, replace existing layers, and reuse some of the geometry creation utilities. And I'll talk about each of those in turn. Oop. It's doing that thing, there we go. Okay, so next, let me make sure that's the right one, yeah. The next thing, once we'd laid out our plan, was to implement the plan. And this is it's a decent sized team. We've got, like 5 people. We had 5.5, depending on the various phases. The money was coming from AWS, direction from the MapLibre group, and then my team was involved, 2 people from AWS and 1 person from Meta, and they put us in charge of it. So they're essentially working for me during the course of the project. And then we also had participation from 2 maintainers, mostly just 1 on the native side. So MapLibre now has these full-time maintainers, which is really great, I have to say. They're busily cleaning things up and getting the CI/CD working nicely and testing and all sorts of wonderful stuff. So we're working closely with the native maintainer, Bart, to make sure that he understands what we're building. So the goal was multi-SDK support. We want to drop in Metal, and in the future, maybe drop in other SDKs as well. Vulkan, DirectX, perhaps, if someone's interested in that. WebGPU for the future, perhaps. Even though WebGPU's got web in the name, it's actually kind of more intended as a multi-platform GPU sort of thing. So we might drop that in as well. But the primary goal was to support Metal. So in the next set of slides, I'll just talk about each of the goals and then how we did. We're actually winding up this first couple of phases of the project, so we're coming to a conclusion here in November, so it's easy enough to say how things went. So direct rendering mode, again, that's most similar to OpenGL. It should be faster than OpenGL if all things else are being equal. We wanted to go for the direct rendering mode, which is a simple one, and then we wanted to also do, if we could, indirect. And this is where you basically hand the data over to the GPU, kind of let it do its thing without telling it what to do each frame. Or at least you tell it what to do in a more abstract way. So the Metal port is working. So we have initial versions. We're seeing similar performance to OpenGL, finding some strange corner cases where it's a lot slower. That's all pretty much expected for real-time rendering. It's been working for several weeks, and it's largely CPU bound, which is not unexpected. So this was a toolkit that was designed back when you didn't really trust the GPU all that much. You gave it very simple instructions. Now things are much more advanced. We should be running on other threads. We should be trusting the GPU. That's still not the case. So it's still largely CPU bound. Indirect mode we haven't gotten to yet, mostly because there's too much going on the CPU. And I'll talk a little bit about that in a later slide. So along the way, we added a secondary goal, which was upgrading to a newer version of OpenGL ES. So there's 3 major versions of OpenGL ES that are interesting. One is the one that's kind of pre-shader. That's back when you had a fixed function pipeline. What that meant was that you could say what the color was, what the texture lookup was on a polygon, things like that, but you didn't have a lot of control over it. OpenGL ES2 added the control. So you started writing shaders, and you started hearing about people doing shaders for very complicated stuff, but they weren't all that sophisticated. That's the version that this version of MapLibre supported, was OpenGL ES2. ES3 added a lot of really great stuff. uniform buffer objects, VAOs, instancing. We're using 2 of those to great effect. And there's a lot more things that could be done as well. Now, Android's still going to be on OpenGL ES for the foreseeable future. So getting all of this moved to 3.0 means that they could upgrade to 3.1 or 3.2 fairly easily, or just use some of the new stuff in 3.0. Again, that wasn't our remit. We're not trying to make the OpenGL version faster, but it was a nice stopping point along the way. All right, so one of our big secondary goals, something that I was really excited about, was trying to make this more user serviceable. Now, I don't know if you've ever looked at the internals of Mapbox.gl, which is now MapLibre Native, but it has a certain style. It's a C++, which is already sounding scary, but it's template, it's C++. So it's a little difficult to understand what's going on just by looking at the code. So I typed into one of those image search engine things, tangled thicket of metaprogramming, and this is what it gave me. So we tried to fix this to a certain degree, particularly around the styling. If you've ever looked at a standard style sheet that's controlling how vector tiles are rendered, you'll see that there's a lot of expression logic in there. So this value changes from 1 to 2 over the course of a zoom level using this equation. All of that gets turned into this very complex ball of template programming within the native version of MapLibre, and it's very hard to break that apart. To essentially say, I'd like to run part of this on the GPU and part of this on the CPU, and tell me when I need to run which on what. So we've tried to make that a little bit better. We've actually pushed the template stuff back, so it's no longer directly associated with the rendering. So the rendering is a lot more rational. Tried to put things near itself. So if you're drawing, for example, a line layer, most of the code should be in one place. And for the most part now, small changes to that logic don't cascade up and down the template stack. But the templates are still there, particularly in the style sheet implementations, and that makes things a little difficult. So in terms of status, yeah. So the first biggest thing is that we can now drop in new rendering SDKs. We did it with Metal, it worked, we didn't have to change too much, mostly it was just a matter of optimization. If you want to drop in a new thing like Vulkan, that should now be possible without us having to do it. The build system's been updated. When you take on one of these projects, you don't hope that you're going to update the build system, but you kind of end up doing it anyway. So it's one of those. It's now on hopefully a little bit better. There's a lot of work done on that side. Shaders are now disentangled, and I'll talk specifically about what that means. That was very complex. And we've beaten back the tangled thicket of metaprogramming, but it's now still associated with the styles. So overall, I think the toolkit is easier to maintain than when we started. In terms of upgradability, so this is something that we were really excited about. We wanted to be able to replace pieces of the native toolkit without having to replace the whole thing or necessarily having to recompile it. So you should be able to add a shader. Again, a shader is the code that's run on the GPU to draw a particular feature. So there's a fill shader, there's a fill outline shader, there's a line shader that does those dashed lines and things like that. These are all components of the system. We wanted to be able to replace one of those without having to recompile the whole thing and make them unique objects that you could actually see. The way the toolkit was before, all the shader source code was stored in a compressed blob, so you couldn't even see it. And when it needed a shader, it would just kind of pull data out of the blob and compile it. It's really clever, but very difficult to modify. So this isn't something you would normally do in an open source project where everything needs to be visible. So we wanted to make it visible. Wanted to be able to replace existing layers, the things that do the filled rendering, things like that, add entirely new layers, perhaps associated with new styles and new features in a style, and add some more examples. So we've mostly been successful there, and we're kind of addressing a lot of this at the end of the project. We can now add and replace shaders, makes debugging a lot easier. And this one I'm particularly excited about. So in most of these maps, you're usually just displaying some GeoJSON or a giant vector map. But most developers will add a little bit of logic on top of that. So if you want to do like a heads-up display, or you want to show where the user is and what direction they're pointed, you're doing that via a custom layer. And that had to be OpenGL before. which, if you think about it, is a little bit silly because all the various things that you want to display, symbols and lines and polygons, they're all there in the toolkit somewhere. Couldn't you just use that to draw it? You couldn't, because it was all intertwined in the way the toolkit was rendering things. You couldn't just pull out a little piece and reuse it. So more recently, we've been working on opening that up. So if you want to write a custom layer, you now can write a C++ layer, which will just draw a bunch of lines and polygons and symbols and all that other sort of stuff. And it's cross-platform, so you no longer have to write OpenGL. So that one's pretty exciting. Old layers are still a little difficult to modify. They're highly optimized, so it's difficult to break them apart. And we're maybe working on some training examples. We'll see how much time we have. In terms of threading, it's really hard to thread something which wasn't designed that way. So this particular goal got deferred, and it was a secondary goal. It's just difficult to do. So you actually can do proper multi-threading with OpenGL. You just have to do it carefully. With Metal, it's much simpler. With Vulkan, it's much simpler. Presumably other SDKs, DirectX, I would imagine it's much simpler. So we won't get to this one in this project, but it may come around again. And I can't emphasize enough how important that is on mobile devices. Typically, the way you work for an app that contains a map is that you should do most of your work off the main thread to let the app developer dominate that main thread for whatever they're doing. We're not really doing that with MapLibre, and it would be really nice too. So this one was it's interesting. When I saw Mapbox.gl when it first came out, I was really impressed with their shaders. I thought they must be doing an amazing job in the shaders because there's all this activity going on. Things are getting wider as you zoom in, things are disappearing as you zoom out. Great shader work. And so we kind of emulated that in our toolkit. When we read style sheets and vector tiles, we did all this work in the shader to make it happen. And then just within the last year when we started digging into it, it turns out they weren't doing anything in the shaders. It's all done on the CPU. It's all very fast, very carefully intertwined in the template logic, but it's all done on the CPU, which is just not how you would do it now. So we've tried to move some of that logic onto the GPU. And it's been mixed. The calculations themselves aren't that complex, talking about how it turned out here. So we can do things on the GPU. We can make the lines change width dynamically based on zoom level. We can make things bigger and smaller. We can change opacity and color. That all works. The problem is we can't get the CPU to stop doing it. All of this logic, which was carefully tuned to change all those data values in real time on the CPU, it's very difficult to turn it off conditionally. So that's something that we continue to look at. And that's why we still have a kind of this tangled web of metaprogramming associated with the styles, is it's very difficult to pick pieces out, move them over, and then throw them away. All right, so for these last few slides, I was going to talk a little bit about where we might be going next. Things went pretty well with this development effort. We got together a team, we managed to get it working, and we've made some positive changes even to the Android version, things that are, I think, going to pay off in the future. So, I'm a consultant. I'm not actually associated with MapLibre. I work for AWS via my company, Wet Dog Weather, and we're looking for new things to do. So some of the things we proposed are put together in some of these slides. So these are discussions that the MapLibre community is having to decide what they might want to do next, assuming there's resources to do it. And it looks like there may be. So there's a category of basically visual improvements. One would be doing a 3D globe. We know how to do that. If the community wants to do it, then we're happy to do it. Cesium 3D tile support would be exciting. That's something that wouldn't be all that difficult if you do other things. Nominally, there is a 3D mode in MapLibre Native, but it's a very simple 3D mode. 3D terrain support, so they already have that to a certain extent on the web, but there's a lot of gesture control that needs to be added, a lot more things you need to do on mobile to make it work right. And then general map coordinate system support. Again, that's something we know how to do, which we'd be happy to bring over to MapLibre if they want it. In terms of performance and expandability, full threading support was something that we threw out there, and a general purpose data loading architecture. So these toolkits were designed around a handful of formats, really just GeoJSON and vector tiles, and it's very difficult to get other data formats into the system. For the web version, they have this add protocol where they can kind of shoehorn things in. But for native, it's a lot more hacky to do that. So if we wanted to add PM tile support, proto-maps, static tile format, it's actually kind of difficult to do. And that actually all made sense back before it was an open source project. They have their pipeline, they want to do it a certain way. But an open source project wants to read as many things as it can. So we proposed a general data loading architecture for that. We'll see if people are interested. OpenGL optimization is still possible. The Android version could be a lot faster, and things of that sort. So there's also other SDKs, WebGPU, Vulkan, and the new Vision OS support. I don't know how popular that headset's going to be, Apple's new headset, but it's at least interesting to think about. And they're also kicking around things related to styles. Do they want to adopt a style editor, for example? And do they want to pursue more optimized vector map rendering? Yeah, all interesting things that they're kicking around. Okay, so what did we learn doing this? Style sheets are complicated. They have expressions in them. They're very difficult to analyze in real time. The engine that was doing that is very difficult to pick apart. Threading support after the fact is very difficult. And there's still lots of room for improvement in the toolkit. Even though we did succeed at getting to metal, performance is going to be at least as good as it was, possibly better. There's still a lot of room for some really impressive performance and new functionality. Also, it should be easier to update components in the system. Hopefully, we made it a little bit easier with our work. All right, so the port was a success. That was good. That was a risk that people took, and we appreciate they took it on us. And it's definitely going to be easier to add more rendering SDKs in the future. So Vulkan is the obvious one, but who knows what the future will bring with this thing. So hopefully this is going to make MapLibre Native a little bit more future-proof. We addressed a lot of the secondary goals, particularly related to opening up the toolkit, making it easier to replace components and add new things, and we deferred several of our other secondary goals. And the sponsors are happy, which obviously is the most important thing to me, and they're looking to do more. So we're waiting to hear back from the community as to what they'd like to do next. All right, that's pretty much it. Questions?